morning all of you. What we are going to cover today in this lecture is the structure of the atom, which is extraordinarily important for all the developments in the 20th century, for that matter even in the 21st century. So, the structure of the atom essentially involves first of all an understanding of the classic experiment by Rutherford when he scattered alpha particles of gold nuclei, what we call as gold nuclei today. And then of course, the planetary model which followed from the Rutherford scattering had to be reconciled with spectroscopic data and with the very problem of the stability of the atom, for which Bohr gave his model. So, in other words, what we are going to discuss in the class today is one of the most crucial developments in physics, because after all, if we understand the basic constituents of matter, the rest of it would be a matter of detail, however complicated it may be. As I told you in my last lecture, the concept of de Broglie waves or the matter waves was actually introduced after Bohr gave his model. In fact, many years after Bohr gave his model. So, historically de Broglie was impressed, he was influenced by these special orbits that Bohr had proposed, and he thought that that could correspond to standing waves of matter waves. But that is not the viewpoint that we are taking in this course, just as that is not the viewpoint that is taken in your 12th standard NCERT course. So, I will return to that concept, but we should remember that the structure of the atom precedes the concept of a matter wave. So, in the last lecture what we essentially did was to introduce the concept of matter wave, and we gave an experimental demonstration of this idea. This was a hypothesis which was put forth by de Broglie, but then Davison and Germer, through their ingenious experiments, were actually able to diffract electrons of a nickel crystal. So, we should always remember the famous formula 2d is equal to 2d sin theta is equal to n lambda. So, the scattering angle is governed by this formula. N is the order of diffraction, d is the spacing between the planes of the crystal, lambda is the wavelength. So, the scattering result was consistent with this formula which is valid for waves and not what they expected of electrons as particles. However, we should remember that experiments with cathode rays, or for that matter even E by M measurements, strongly suggest, in fact they provide great evidence that electrons are actually very tiny particles. So, again we have the same dilemma that we encounter, the same duality that we encountered in the case of light. With interference and diffraction it behaves like a wave, and with regarding to photoelectric effect or Compton scattering it behaves like a particle. In a similar manner, electron when it is getting accelerated by voltage, when you are looking at its tracks in a magnetic field, etc., behaves like a particle, but then when it is scattered off a nickel crystal, then it shows beautiful diffraction patterns. So, we have to remember that. Before I go on to discuss the structure of the atom, I want to round off a discussion by cautioning you on how careful we should be in using the concept of wave, especially when it comes to matter wave. So, let me recollect what we have done both in the case of light and in the case of matter. So, let us start with light, electromagnetic radiation. So, in the case of electromagnetic radiation, we have two important expressions, E equal to h nu, and the second expression is obviously given by V equal to c. All wavelengths propagate with the same speed given by, denoted by c, which is 3 into 10 to the power of 8 kilometers per second, and this is nothing but nu lambda. In other words, when we associate an energy with a frequency nu associates an energy E, We are also associating the same energy with a wavelength, because after all my nu is nothing but c by lambda. So, it is entirely a matter of taste whether you want to relate energy to frequency or energy to the wavelength, at least at this particular point, and therefore I can write E is equal to h c by lambda. That is what I have. So, in my lectures on photoelectric effect, I also argued that it follows from classical theory. All this is Planck. So, it is as if we are riding two horses, sometimes that of Maxwell and sometimes that of Planck. Now, if I come back to Maxwell, the age old wave theory, which of course has a great experimental evidence, Maxwell says that if you have a monochromatic plane wave, let us say, then the energy density is related to the momentum density by a factor of c. So, this is energy density and this is momentum density. So, what do I mean by energy density and momentum density? That is the energy per unit volume carried by the radiation, and momentum density is the momentum carried by the radiation per unit volume. That is what we have. Now, Mr. Planck would like to associate a certain number of particles corresponding to this and corresponding to this. So, if you have an energy density corresponding to radiation of a given frequency, so if you want I can put the subscript nu here. If I did that, then what we would do is to introduce the number density of the photons. Number density of photons. We now couple this number density